Nevada's high desert is defined by its fractured, barren topography. Yet concealed beneath these arid basins and ranges lies one of the highest concentrations of wealth on the planet. This map shows the alignment of the Carlin-type gold deposits. This highly specific north-to-south geometric corridor currently accounts for nearly 9% of all global gold production. But the ore extracted from these zones presents a severe paradox. Standard gold deposits usually announce themselves with thick, glittering quartz veins and visible metallic flakes. Carlin-type ore, by contrast, is a drab, silty carbonate rock. It looks exactly like worthless roadside gravel. This radar chart quantifies the contradiction. Standard epithermal deposits have distinct footprints: high copper, lead, zinc, and thick quartz. Carlin-type deposits register massive gold grades, above 10 grams per ton, yet contain zero visible gold, zero quartz, and near total base metal depletion. Because these deposits entirely lack traditional metallic halos and visual cues, standard exploration models cannot detect them. Geologists using epithermal blueprints will walk directly over millions of ounces of gold and never know it is there. The gold in a Carlin-type system is invisible because of where it physically resides. It is locked as submicron particles, trapped deeply inside the crystal lattice of a mineral called Arsenian pyrite. This unique microscopic mineralogy is not the byproduct of a single localized magmatic event. It required a 600 million-year chronological stacking of highly specific structural and chemical prerequisites. We can break these prerequisites into three distinct phases: ancient tectonic preconditioning, specific fluid dynamics during the Eocene epoch, and the modern multiparametric geophysics required to map the fallout. To find a blind Carlin-type deposit, we have to physically construct its tectonic history from the bedrock up. We must map exactly how ancient geologic stress directs modern geochemical signals to the surface. This 3D block model illustrates the base foundation of the crust during Neoproterozoic rifting. On a passive continental margin, layers of highly permeable silty carbonates were deposited on the ocean floor. During the Paleozoic antler orogeny, violent tectonic compression forced deep marine eugeoclinal rocks to thrust eastward over the established continental shelf. The structural result of this collision is absolute. Dense, impermeable siliciclastic rocks are now physically stacked directly on top of the highly permeable carbonate foundation. This specific tectonic contact zone, known as the Roberts Mountain Thrust, creates a regional aquitard. It is a completely impenetrable roof over the carbonate sequence. Since fluids cannot punch vertically through this dense cap, upwelling hydrothermal liquids are violently forced to spread laterally through the reactive, porous carbonates below. Without this precise tectonic capping event millions of years prior, future gold-bearing fluids would have simply vented to the surface and dissipated. Instead, the regional aquitard traps them underground. The next requirement in our timeline occurs during the Mesozoic, when widespread magmatism drove vertical igneous stalks up through this stacked sedimentary sequence. Once cooled, these igneous intrusions act as unbreakable solid nodes. They are physically suspended within a matrix of softer, much more pliable sedimentary rock. We now jump to the Eocene epoch, roughly 40 million years ago. As the Farallon tectonic slab was removed from the base of the North American plate, northern Nevada experienced a massive, region-wide west-northwest crustal extension. This stress model shows the mechanical reality of crustal extension. Pulling the crust apart tears the softer sedimentary rock, and that tearing concentrates specifically around the edges of the unyielding igneous stalks. This creates localized areas of reduced effective mean stress, effectively generating vertical highways of heavily fractured open void space. The Mesozoic magma did not supply the gold. Its physical rigidity allowed the later Eocene extension to weaponize the bedrock, creating the perfect structural plumbing system for fluid migration. With the plumbing established, deep hydrothermal fluids begin to rise. These fluids are moderately hot, loaded with dissolved gold, and highly enriched in hydrogen sulfide. The fluid races up the fracture meshes at the edges of the igneous stalks. When it hits the impermeable regional aquitard up atop of the system, it is forced aggressively sideways into the reactive silty carbonates. Here, the first chemical reaction triggers: decalcification. The acidic hydrothermal fluid dissolves the carbonate rock matrix. This causes severe volume loss and drastically increases the rock's porosity, turning it into a microscopic sponge rather than forming large open caverns. As the rock dissolves, it liberates reactive iron into these pores, triggering sulfidation. The fluid's hydrogen sulfide reacts instantly with this iron, precipitating Arsenian pyrite crystals. This growing pyrite strips submicron gold from the solution, locking it permanently within its crystal lattice. This entire chemical replacement process occurs internally. It leaves the exterior of the host rock looking visually dull and unaltered to the naked eye, perfectly camouflaging the massive wealth inside. Modern exploration relies on the fact that this subterranean decalcification and sulfidation process leaves a highly specific microscopic chemical bleed on the surface. Because Carlin-type systems operate through this unique replacement chemistry, looking for standard epithermal copper, lead, or zinc halos will result in drilling dry holes. This target map illustrates the core geochemical anomaly. Directly above the ore body lies a tight concentration of gold, arsenic, mercury, and thallium. Surrounding this, a broader halo of arsenic, antimony, and mercury remains highly anomalous, indicating a nearby system. Thallium and arsenic are the absolute diagnostic fingerprints. Their presence at the surface proves that Carlin-style sulfidation has successfully occurred in the crust below. We must also resolve the geophysical paradox. How does a massive concentration of heavy metals register as a physical void and a magnetic dead zone? This BRID block model shows the geoelectric signature. Induced polarization, or IP surveys, actively detect the disseminated Arsenian pyrite, returning a medium-high chargeability rating exactly where the fluid migrated. Resistivity is counterintuitive. The porous core drops resistivity, while jasperoid edges create sharp spikes. Geomagnetics reveal a magnetic low where fluids destroyed primary magnetite. Finally, extensive decalcification dissolved the rock's mass, creating a gravity low exactly where gold is trapped. To a geophysicist, a Carlin-type deposit doesn't look like a solid, heavy mass of gold. Instead, it's a structural void, stripped of its magnetism, hiding a highly chargeable battery of pyrite. This digital elevation model reveals how modern exploration begins. Analysts scan these low-relief terrains to locate subtle surface drainages and linear valleys, the surface expressions of deep, cross-cutting structural corridors. Geologists stack inverted geophysical data onto structural intersections, mapping the overlap of magnetic, gravity, and IP signatures. The final constraint is chemical. Drilling occurs only where this stack perfectly overlaps a gold, arsenic, mercury, and thallium surface anomaly. These massive technological and geological operations occur in environments that, from the highway, look entirely empty and undisturbed. The Carlin-type deposit remains physically invisible to the naked eye. But it becomes mathematically undeniable when you align a 600 million year tectonic history with precise multi-parametric geophysics.